All right, so I'm going to get started here on the final review questions for the term test. I'm going to be going over a retaining wall question and a rate of consolidation question that I feel like would be important for you guys to understand. I'm going to be going over the retaining wall question from the white test of term test 2, which was question 4, mainly because there was a bit of confusion on how to do the moment arms, how to find the factor of safety for overturning and for sliding. And when I took the course, this question was both on the midterm and the final, so I wouldn't be surprised if he decides to do that again. So the questions I've posted in the announcements where you would have found the placeholder. So if you want to bring that up so you can kind of reference where I'm getting these questions from. But basically we have a retaining wall that looks like this. And the dimensions are as follows. So first thing that we need to do is find the forces generated from each of our. So what I'm going to do is, hey Pat, I'm doing a video tutorial right now, by the way, just so you know. No worries. So the first thing that we need to do is find our forces. So we know that we have our passive force right here, which is the force on this side here. Next, we have the two forces generated from our retaining wall. So I'm going to break them up as kind of this bottom chunk and this chunk here. And finally, our active force here. And then for our moment arms, I'm just going to kind of draw in the centroid so I can refer to them later. Which are a third of the height from the base of the triangle. So the first thing that we're going to do is find our Ka and our Kp. So we know that Ka is equal to 1 minus sine of phi over 1 plus the sine of phi. And we know phi is 30 degrees from our question. Which we get as 1 over 3. And we know that Ka times Kp is equal to 1. So Kp must be equal to 3. Now this relationship here is only true when the slope above our retaining walls are both equal to 0. So this slope here, beta, is equal to 0 degrees. Because there's no slope, right? It's just flat there. And again, same with our slope here is also equal to 0, right? So that's the only reason why this relationship here is true. If not, for example, let's say Ka did have an angle then you'd use that big long equation that has tons of coses in it. You guys can take a look at your final formula page to get an idea of what that equation looks like. And then you can use this equation, but it's the inverse. It's also on your equation page to find Kp. And then this relationship would not be true. But because the slope of both of these are 0, then it is true. Next, this is something that some people were confused about. So actually, I'll get to that when we get to the sliding. So first, we're going to find our force generated from our passive force. So F1 is equal to 1/2 KAH squared, which is 1/2. Our unit weight of the sand is, I copied over the wrong, my apologies. Okay, I'm gonna update the, I'll do it once I'm finished the video. The questions that I've provided, I put on the yellow question 4 by accident. So I'm gonna be getting values from a different diagram here. And then I'll update, once I finish the video, I'll update the announcements with the proper questions. That's my bad, sorry about that. So the unit weight of the sand for this question is 17 kilonewtons per meter cubed, not 15. Ka we know is 1/3. And the height of our Ka here is 8 meters, so 8 squared, which gives us 181.3 kilonewtons per meter. Our F2 is 1/2 gamma Kp h squared, which is 1/2 times 17 is our unit weight. Kp is 3, and our h is 2 meters squared. Because if we look, we know that for our passive force, the height here is 2 meters, which gives us 102 kilonewtons per meter. Then for our force 3, we are finding the area of that force and multiplied by the unit weight. So for 3, we have 0.5 meters. Actually, just to clear this up here. I did it right. Okay, yeah. So the diagram here that I've drawn right here, this diagram is the right diagram. So you can follow this diagram with this, but don't look at the question that I've posted in the Word document. I'll change that when I'm finished the tutorial. So we have 0.5 meters in width, and I kind of cut here. So it's 8 meters minus this 2 meters is 6 meters. So 6 meters. And then multiply by the unit weight of concrete here, which is 28. And that gives us 84 kilonewtons per meter. For F4, similar, 2 meters times 4 meters, because this height is 2 and this length is 4. And then we multiply that by the unit weight of concrete, which gives us 224. So for the factor of safety for overturning, we're looking at the moments generated by each of these forces. So when you look at our diagram up here, you can see that you can see that force 2, 3, and 4 are acting in clockwise direction, and force 1 is acting in the counterclockwise direction. Since we know that the retaining wall won't be overturning this way because there's all this soil here, so it's impossible for it to fall into the ground. The only possible way that it can overturn is by overturning this way and coming kind of out of the soil, sort of like that, in that direction. So we're looking to see the factor of safety over that. So we're going to do clockwise over counterclockwise. So we're going to be the moment generated from force 2 plus the moment generated from force 3 and force 4 over the moment generated from force 1. So from 2, we know that our force is 102 kilonewtons. And the moment arm generated from force 2. So we look here at force 2, and we see that it's a triangle. So a triangle acts from the centroid at a third of the height from the base. So the base is here. The height would be this 2 meters. So it's a third of that height. Oops. So then it's a third of the height. So 2 over 3 meters. For our moment arm for force 3, so this is probably the most confusing one. So we know our force is 84 kilonewtons. So to find the moment arm, this is the best way that I can explain it. So first, we know that it's acting through the centroid of force 3. But we're looking for the moment arm from this point. Let's say it's called point A. So it's going to be this whole distance minus half of the width of 3. So, or another way you could look at it is from the start of 3 and then halfway across to the middle. So I'm going to say 4 meters minus 0.5 meters to get to the sort of initial starting point of force 3, and then halfway of the width of force 3, which is 0.25. Another way you could look at it is from kind of the end of 3, which would just be 4 minus 0.25, but whatever, it gives you the same answer. And then adding in also the moment from our force 4, which is our force 4 is 224 kilonewtons, and our centroid of force 4 is this. If this length is 4 meters, it's half of that, so it's 2 meters. And then that's all. Those are all of our clockwise moments. So now our counterclockwise moment is generated from our force 1, which our force 1 we calculated as 181.3 kilonewtons, and then we multiply that by 1/3 of the height from the base of the triangle. So the base of the triangle is here, the height is 8 meters, so it's a third acting, so 8 over 3. Which gives us a factor of safety of 1.72. So for sliding, we're basically doing a horizontal force balance on our retaining wall. So just a quick little sketch here. If this is our retaining wall, we've got the forces, the normal forces from our force 3 and force 2, and then we've got the direct forces from our force 1 and our force 3. And we're doing it for sliding. So we're looking if it's going to be moving in either of these directions. So the force from our passive and our active forces are going to be directly acting on the sliding, but the forces from our normal forces are going to be needed to multiply by some coefficient of friction to figure out what the frictional force acting is. So again, we know that it's not going to be sliding this way because there's this big chunk of soil here and it can't push that whole chunk of soil. So if it's going to move, it's going to slide this way. So we're looking for it going against that. So then our forces that go in the opposite direction are force 2. And then we're assuming that the frictional forces are going to help us keep it in place. So our force 3 and our force 4, but they're normal forces. So they need to be converted from the vertical direction into the horizontal direction by multiplying by the provided value of mu, or coefficient of friction, there. And then the force that would cause it to slide would be force 1, which is going to be on the bottom. So just to clarify, this value, the coefficient of friction, can be also explained as the angle of friction. But the angle of friction would be provided in degrees. So the relationship then would be tan angle of friction is equal to mu. So if you were provided with an angle of friction, then you would just use, instead of mu, you would put tan of the angle of friction here. But we're given mu directly, so we can just multiply the normal forces into frictional forces. So our F2 we solved as 102 kilonewtons. F3 is 84. F4 is 224. And then we need to convert these from normal forces to friction forces by multiplying by our coefficient of friction, which is 0.36, all over 181.3, which is our force generated from our active force, which gives us 1.17 for our factor of safety for sliding. So again, you know, he did have this on both my term test 2 and my final last year. So it's important to know how to get these forces, but then also equally as important to know how to get these moment arms. So, you know, if you're having trouble, maybe Google some moment arm, simple, you know, mechanics 1. It's okay to forget that stuff. I mean, for most of you, it was 2 or 3 years ago, so it's not necessarily the easiest thing to remember, but you definitely need to know it. So the next question I'm going to go over is question 11.10. And question 11.10, you don't necessarily need the diagram that I provided, but it refers to it, so I put it in there. This is a rate of consolidation question. And right, so basically there's this fill. So I'm just looking at 11.29. If you want to look at it with me in the Word document, this one is good, so it's going to remain the same. So there's this proposed fill that they're putting in to settle the soil, and we're assuming that the ultimate consolidation for the settlement is 1.6 feet. So you put the fill on, and then the ultimate consolidation for the fill for the rest of the soil is 1.6 feet. And the owner then wants to build a structure on top of the fill. And the structure can withstand a total sediment of 4 inches. How long must the owner wait after the placement of the fill before building the structure on top of the fill? So basically, we know that our ultimate consolidation is equal to 1.6 feet, which basically means that before the fill is there, the consolidation is 0. You put the fill on, and after an extended amount of time, the soil will consolidate 1.6 feet, and it will not consolidate past that, right? Then we know that the building he's trying to build can withstand 4 inches of consolidation. 4 inches. That's good. So what we need to do, because we're trying to find how long he has to wait after the placement's been placed before building the structure on top. So we know that then the amount of settlement that needs to happen before you can place the building would be equal to our ultimate consolidation minus the amount of consolidation that the building can withstand. Because basically what that means is the building can withstand 4 inches, so it needs to consolidate 1.6 feet, which is the total, minus the 4 inches. Then it will consolidate 4 inches, and then it will reach its final consolidation. So then we're looking to see how much consolidation needs to happen before we can put the building on, which would be 1.6 feet of consolidation minus the amount that it can withstand, which is 4 inches. Now I'm going to convert that to feet times 1 foot over 12 inches, which gives us 1.27 feet. So again, just so that you guys can kind of understand this, basically this delta subscript C is the amount of consolidation that needs to happen before we put the building on, and this is the total because it can withstand 4 inches. So it's 4 inches less than the total is what needs to happen. So then we're finding kind of the ratio of that, which is our U, and U would then be equal to our consolidation before the building over our total consolidation, which is 1.27 feet over 1.6 feet times 100%, which gives us 79%. So, just so this is clear again, you put the fill on, it's not consolidated yet. Instantaneously, it hasn't consolidated. It starts to consolidate, gets to 50%, then it gets to 79%. Now that means that 79% of the total consolidation has happened, but the building can withstand 21% of the total consolidation, which is the 4 inches. And that's why we have to wait for 79% of the total consolidation to happen before we can put the fill on, or the building. So then we need to find, it's asking to find how long owner must wait after the placement. So our equation with time is TV equals, CVT over HDR squared. Based on our diagram, we're given CV and HDR. We're trying to find T. So we need to find what our TV is. There's 2 equations that relate TV and U, but we know that since our U is greater than 52.6%, U must be equal to, actually I'm going to write it down here because it's kind of a big equation. 1 minus 10 to the power of 0.085 plus TV over 0.933 times 100%. And we know our U is equal to 79%. So everything else is just constant numbers. So then when you solve, we get a TV is equal to 0.547. So then we go back to our equation for TV. TV is equal to CV T over HDR squared. We know our TV is equal to 0.547. If you look on our diagram, it gives us for the soft clay the CV, which is 0.17 feet squared per day. We're looking for the time, and our HDR squared would be 25 feet. So so people understand, I'm going to put it on the bracket, so people understand where I got this 25 from. So the height, the HDR is the drainage height of our soil. So we're looking at our soft clay, and if you look at the diagram, under the soft clay is a stiff clay, which we assume impermeable. So when you are consolidating, you are basically squeezing the void spaces out of the soil, and but that air or that water needs to go somewhere. So if you're assuming that it's impermeable, the water or the air can only get out, as we're assuming this is impermeable that I just drew, then the water can only get out this way. So the total distance that the drainage would be the entire height of this. Whereas if this wasn't impermeable, then the water could go out either direction. But obviously, if it's above, it's going to prioritize going this way, and if it's below the center, it's going to prioritize this way. So if it wasn't an impermeable stiff clay, then the height would be 12.5 feet. But since this is impermeable, then it's total height. So yeah, and then we solve for T, which gives us 211 days, which is roughly equal to 5.5 years. So basically what it's saying is that after you place the proposed fill, there hasn't been any consolidation yet. After 5.5 years, it's going to consolidate to 79% of its total consolidation, which is 4 inches less than its total consolidation. And since our building can withstand 4 inches of consolidation, we're going to build the building after 5.5 years. It's going to continue to consolidate, but it will be able to stand that consolidation. And yeah, so that's question 11.10. I'll be in my office basically up until the midterm, today until probably 5 or 6, and then tomorrow from 3 to 4 I have a meeting, but otherwise I'll be here. So if you guys have questions, feel free to come. Hopefully this video tutorial will be helpful, and study hard, and good luck on your midterm. Thanks for watching.